There you go.
Thank you so much.
You're welcome. So the molecules and materials are collections of ions and electrons, and one needs to solve Schrödinger equation for them. And since there are so many electrons, so many ions, one needs to split equations for ions and electrons. And half of the, or about 30% of our time, we were dealing with ions, and the rest of the time we were dealing with electrons, so with the goal of reduce Schrödinger equation for so many electrons to somewhat simpler. And the first heroes who were able to derive such theory were Hartree and Fock, who derived a theory that maps, projects the multi-electron problem onto efficient one-electron problem, where the electron-electron interaction is taken into account through self-consistent procedure. And you are presenting how to run computational software based on this theory with a great success. Now we are in the middle of the chapter that deals with workhorse of computational chemistry, whose name is, the name of this horse is density functional theory. So it is a theory that is not the most precise one, but it provides an excellent balance between numerical resources and numerical resources and the precision. So we have started to go over this chapter by looking onto some background theorems that introduces the concept of total electron density and tells that many of the tricks that we were doing for these wave functions can be done on the language of electron density. So there are two major theorems. One theorem is that everything in a specific molecule can be found based on a density, which sounds strange, but we found it by using mathematical tool for ad absurdum from idiotism. And the second theorem was that if one does have absolutely correct density, then one will have absolutely minimal energy, total energy of the system. And if the total density is modified a little, then energy will grow. So anyone wants to object on this statement? No. Okay, so from the theorem, it means that if you have some slightly wrong density and slightly higher than needed total energy, then we can launch a surge, a self-consistent procedure that will improve density and improve energy until it will converge to ideal optimal value. That's it. Now you know what density functional theory is in principle. And we need to go through the details. So to implement the ideas into equations that a programmer whom we hire would type in and as a code and let us use it. So please digest this idea, and before we go to the actual material, I am going to make some administrative announcements regarding the course. So some of you have already submitted homeworks by emails. From some of you, I am hoping to collect it by walking through the rows. And there will be a set of presentations where you'll share skills that we are accumulating in the labs that you are visiting by your free will. I have updated the list of the subjects, and main goal of today's meeting, in addition to theory, is to practice democracy. So there is a list of presentation titles that please make a couple of choices, like choice 1, choice 2. And then we will try to make everyone happy or minimize number of unhappy people. So you can start looking through it, and I will go through the list in more details as we go. So the course consists of 4 chapters. We are done with 2. We are in the middle of the 3rd. We are going through Kohn-Sham algorithm and the presentations that you are practicing democracy and filling in. So I'm going to get this piece of paper back at the end of our meeting. Will result in presentations on November 10th. That you will split practical skills on small itemized parts, and each individual becomes expert in one of them and shares personal history of successes and failures with others. And it seems to be helpful to get better idea in the practical skills, better than exams or homeworks, although we do not decline those traditional forms. So originally we were planning on November 3rd, but it is too early. Let's plan on November 10th as we cannot shift it later. 10th for sure. And then in the rest of semester, there will be also a little research project component that we need to have like 3-4 weeks to complete it. Okay, so here is the list that you are populating right now. So I was trying my best to minimize the list of the skills with the WASP software so that we spend as less time as possible and get as much functionality as possible towards research projects, but it cannot be compressed too much. There should be some important components. So I have included whatever is needed to describe optical properties, electrochemistry, and reactions. Many important things are skipped, but we need to fit in time. So the red stuff is what we already did in the homework that I'm going to collect and in the previous lab. The blue one is what will be in the coming lab, which will be either in person or through a remote connection. And the green one will be on November 2nd. So those are 3 important components. The black one, as time allows. They are relatively short and we can fit them in whatever time remains. So components of computational skills for finding total energy, estimating ionization, estimating absorption spectra, looking for desorption energy during reactions, and things like this. So please lean back and do not concentrate yet. It's not yet time for peak intellectual concentration. I am going to give a little heads up towards one of the subjects that you will see there, and that is already covered in the that will be covered in our next lab tomorrow. So this piece of software, Vienna Ab initio software package, is designed to bridge chemistry, molecules, maybe large biomolecules, and solids, surfaces, substrates in the physical and engineering sense. So one of the features of such models is periodicity. So they are infinite and periodic. And simplest model that has this feature are one-dimensional polymers. So in the models that we were doing at homeworks, we were missing those. We were doing oligomers with few monomers stick together, but we were not covering infinite chains. It is time to approach it. So we will take one of the oligomers from your homework, measure its size, identify a periodic cell that is repeating, and compute the adjustment, the size of the bond that is needed to make it repeated. And then by preparing the simulation cell, we will compute the total density and we will see the molecule is infinite. So one explicitly treats only the one box, but it implies that there are copies of these periodic images and it is infinite to the left and to the right. So one can describe infinite polymers or polymers of lengths approaching infinity. But it is not for this meeting, it is for the lab. And it's just a little heads-on what we will be doing in the last month. So, science and in general and computational chemistry in particular doesn't have goal to dry brains of young people. It is designed by people for the people. And all people who design these theories and program codes have their strong and weak places. They have biographies and birth dates. So, and sometimes if they perform well, they get awards for their performance. So this smiling face is 93-year-old Walter Kohn, who got Nobel Prize for actually designing the density functional theory that we are considering today. And it's just some facts from Wikipedia showing that not everything was perfect. Not everyone was accepting him from the beginning. And another thing that I was surprised to learn that his original background is related to math. So it gives us a little understanding why the density functional theory includes formulation of theorems. Okay, and here is the plan of our meeting that I'm going to cover. So we will try to go over either slides or some blackboard scratching, and I will announce completion and progress of each statement in this plan. So, as we were discussing before, density, so I'm starting with the first item in this plan. Comment on orbital free density function theory. So, as we were discussing before, in density functional theory, we are departing from wave functions and Hamiltonian operators. Instead, we are using densities and functionals. And if we are purists, if we support the idea of density functional in 100%, then we are not allowed to have wave functions, we are not allowed to have orbitals. And such pure people do exist, although it is minority, but there are people who develop so-called orbital-free DFT. And it is not us. We are going to be a little more conservative and practical. But there are people who believe that density functional theory is absolute, and they do not accept even a word orbital or wave function. It's not practical for chemistry. It is good for warm matter, like plasma in the center of sun or like nuclear explosions. Then it's hard to draw orbitals. Everything is so mixed up. But in this orbital-free density functional theory, it is purely as we illustrated in Thomas Fermi. There is only density and only energy, nothing else. Only density and only energy. But the main achievement, and I think the Nobel Prize was assigned to Kohn and his collaborator Popel, who is author of Gaussian software, not for the theorems. I don't believe you can get Nobel Prize for theorem. For algorithm. So although those theorems are, I think he designed theorems after, but main thing, he designed an algorithm. How to improve total energy and total density to an absolute. So an algorithm that allows to converge from whatever we guess to be a density and energy to something that is approaching what is on the nature. So a little reminder, if some of us were not fully attentive on previous lectures, you can cover it in 20 seconds now. So 2 lectures ago, we considered that as soon as we know distribution amount of charge density in each point of space, we can retract back which ions did create this charge density. So one can solve the back problem. And then from positions of ions and this potential, one can reproduce total wave function and Hamiltonian. So meaning that if we know density, we know everything. And second theorem is that any density except the true one will have energy higher than the minimal energy. Theorems are proved, but there are not a single word how to find density and how to find energy. So we are going to go through this plan, and we need to justify, we need to be a little more practical and conservative and still use concept of orbitals, which are very intuitively helpful, and they are easy to compute and go over. And we will set up a merger of true density functional theory and a little bit of Schrödinger equation. In order to do this, we will need to introduce a couple of new concepts. So so-called concept of functional derivative. And we are going to introduce a parallel universe, which is not for the first time in our course. We introduced several parallel universes, and 1 course ago we introduced some of you were taking physical chemistry. There one introduces a universe that has nothing except 1 electron. Okay, it's very a dream of a theorist. Then in this course, 3 meetings ago, we introduced a parallel universe of Thomas and Fermi, who have infinite universe, split it on little cages, filled with silly electrons. Silly because they forget to interact with each other. So a universe of non-interacting electrons. Now we are going to introduce another parallel world, which will be indeed much more practical. So it will be a universe that does contains nuclei. So molecules are allowed in this universe. But electrons still forget to interact with each other. So there will be many of electrons, but they will feel only attraction from nuclei, and they will come through each other without noticing, without saying hello. And after we discuss this parallel universe, it will be a key cornerstone to set up an algorithm for success, for computing electronic structure of anything based on density functional theorems. So at the end of the meeting, and we definitely will finish in 1 hour as scheduled. I think it is plenty of time. So within 1 hour, we will set up an idea of a loop with a self-consistent increment. A little improvement of density leads to, through some steps, a little improvement of energy, and then going in cycle-wise until we have matching of convergence criteria. Why orbitals are good? Because it is very strict procedure how to compute kinetic energy out of those. So if you do have orbital, and we apply operator of kinetic energy, which just second derivative over position, it immediately converts this orbital into kinetic energy multiplied by energy. So it's multiplied by orbital. So it is well-established procedure that doesn't induce double doubts in anyone. So the plan is to use concepts of orbitals because they allow to compute kinetic energy. For the rest of energies, we will still be loyal to ideals of density function. Okay, now it is time to stop mumbling over boring slides and scratch something on the blackboard. Let me see if the system, no, the recording is not perfect today, but we can deal anyway. So we are going to introduce concept of functional derivative. When we were starting to discuss density function theory, we introduced concept of function as an extension of concept of function. Function now is better than function. But since we do have derivatives of functions, there should be analogous concepts, derivatives of functions. Another concept that we went through, that if we do have, let's say, electron to nuclear interaction, so negative attraction, charge of ion, distance from electron to ion. And here, in order to complete this expression, we need to multiply it by density of electrons and integrate it, right? Please object if you do not like this expression, if it sounds unnatural. So it's simple Coulomb energy. Charge of ion, charge of electron in a given point in space, and Coulomb denominator with minus sign. Nature. Now one does call it external potential that depends on position of electron. So we tell it expectation value of electron to nuclear interaction is integral of this external potential times density. No objections.
Is there a summation sign?
Summation sign is included into this external potential. So it includes interaction with all ions. Okay?
Yeah.
A little trick. So density of electrons in a given point of space multiplied by size of our volume element can be interpreted as increment in density. Maybe a little crazy, but formally correct. And we still keep the V and integral sign. So if we integrate potential, now we go from true space to space of possible densities. Very multidimensional space. The integration of potential over different densities. Then we get total energy. What if we remove integral and consider infinitesimal change of the total energy of electronuclear interaction and infinitesimal change of the density? So d rho So your calculus teachers would not object. Okay. And now we do high school algebra. We divide both sides by delta rho. No objections. And since we are doing something crazy, which differs from regular calculus, we are allowed to design crazy symbols. And maybe even use some crazy words. So let's use, instead of dV, this fancy delta. So it is, how do we define regular derivative? It's limit of increment of function in respect to increment of argument, right? Something like this. We can write limit of increment of functional, right? This is functional, of functional, in respect to increment of density. And we can, by analog to calculus, there we have just derivative, and since here we have functional derivative. I fear the subject a lot. It was like I was bouncing back for several years. But if you do not have conflict, you are happy too. So we just do increment of function to increment of density, and this will be functional derivative, and it will provide the potential. This one. Potential of with which potential electrons interact to nucleus. So it means that from some unknown sources, we already know the functional, which should be rectangular brackets, and we know how to do functional derivative. We can immediately reproduce potential of electron to nuclear interaction, and we can reproduce positions of all nucleus. Why? Why did we spend 5 minutes on this crazy concept? Because it is a bridge from this new concepts to our old favorite simple one electron potentials that can be easily stick into Schrödinger equation. So the benefit, it is usable for Schrödinger equation. No objections. I deserve a sip of coffee. And something similar is scratched here. So increment of functional in respect to increment of derivative gives the potential. So we are done with functional derivative, and we are already got the benefits that it does help to use our strong skills in Schrödinger equation. Okay. So, what are components, what are terms in the total energy? This is something that you're probably tired of because we repeat it anytime. So it is T and V letters with little abbreviations which indicate electrons and nucleus. So total energy is T electron, kinetic energy of electrons, VEN for electron-nuclear attraction, and then electron-electron, VEE, electron-electron interaction, which, as we know from our experience in Hartree-Fock theory, can be formulated as direct Coulomb and exchange term. And main approximation of Hartree-Fock is that one is missing so-called correlation energy, which means that if you have two electrons moving around, say, nuclei, they feel each other and they try to be on the opposite side, like hide and seek. And Hartree-Fock orbitals do not know about it. They are silly coming through each other. But all the electron terms, interactions, they do not depend on where ions are, which means, and they do not depend on what are kinetic energies. So it means that they are universal. And one can set up this functional once and forever for any molecule. Here just a little comment on correlation. So if we do not have correlation, then product of two densities would give density of two independent variables. But this is not always true. One can design some like function, two-dimensional function, which will differ from just product of two components. But sometimes it is important. Okay, where are we now? We are going to speak about parallel universes right now. I'm going to reproduce what you see here, but it will be more vivid if I draw it, if I write this couple of lines from scratch and we speak about them. So consider that we have true universe, parallel universe, and Walter Kohn, who got mathematical background, does have a transition between these two universes. It's transition. So in the true universe, total energy is functional of density is kinetic plus interaction to ions plus electron-electron interaction. What Walter Kohn has suggested that if you own $100, it doesn't matter which nodes represent your ownership. You can have them all by $1 bills, or you can have like 5 times 10 and 50 times. Or you can have all of them 10 times 10. So how the total sum is accumulated doesn't matter. So he keeps kinetic energy and electron-nuclear interaction virgin. He doesn't play with it. But for the no, I lied. He does a trick to electron-nuclear interaction. And then he tells that why don't we set up a specific parameter, lambda, which will be smaller than 1 and equal to 0, and we will multiply the electron-electron interaction by this parameter. So no physics, no chemistry, no biology, just pure math. If lambda equals 1, then we get back to true world. But there are theorems, and there is understanding that we are not allowed to tweak the total energy and total density. The total sum that we own, we do not have right to change. But the way how it is accumulated, not a problem. So he suggests if we slowly decrease the value of lambda, but we want to keep the same value of total energy, we should slowly increase the amount of electron to nuclear interaction. So if electrons do not interact, maybe to compensate it, there are a little more attractive ions that induce stronger energy of interaction. And then we are coming to a limit when this parameter lambda is equal 0. So we still keep the same density and the same total energy. But we are accumulating this total energy only as summation of kinetic energy plus electron-nuclear interaction with subscript lambda. Subscript lambda means it is not a true, it is not electron-nuclear interaction from the real world. It is some electron-nuclear interaction from a parallel world, from the auxiliary world. So it is a CHEM universe where we have no electron-electron interaction, just because of this mathematical trick. So suppose, why don't we assume parallel universe? And I think CHEM, it was his greatest student who put it in more details before they discussed the main ideas. We are almost done. Well, we still need to stay here and go through details, but the main idea is here. So if we can formulate a function of total energy in interaction in this CHEM universe where there is no electron-electron interaction, then we can use all of our power to solve one electron Schrödinger equations. Because Schrödinger equations for true molecules are hard to compute because they do have electron-electron interaction. As soon as we remove it, happiness comes to us. The energy, we can use all of our skills. To solve Schrödinger equation. So everything proves that although we believe in density function theory, we have proved theorems, but we will use our skills to solve Schrödinger equation and get healthy benefits of it. Just one more equation to continue this idea. We are going to use our skills to compute kinetic energy based on previous experience. It's not a very big deal. We'll do it. Therefore, for kinetic energy term, we will do something old-fashioned. So we will need functional only for the electron to nuclear interaction in CHEM world. Therefore, we are going to, very soon, we are going to write down electron-nuclear interaction as a subtraction of total energy minus kinetic. Right? So it's nothing new, but if you add a little formality, what we do. Total minus do we have all components to formulate the algorithm for improving density and energy? Well, we want to be optimistic and we would like to have it ready, but no, we are not yet. We have almost everything related to energy, but we still do not know how to process the density. So suppose we return back to old-fashioned Schrödinger equation. We find orbitals, whatever, multi-electrons, single electron, but how do we construct density? We have a general idea that absolute value squared of the orbital gives density. But are there any specialty? How does one changes this protocol to compute charge density if you have multi-electron wave function? So in order to have all components, we need the next step. We need to get well-approved algorithm for extracting, for writing down exact total density from orbitals or whatever we have. How are we going to do it? So we like to explain everything in simple terms, but there are some background concepts where one needs to be precise. And those background concepts are antisymmetry of electrons due to spins, and therefore multi-electron wave function is a Slater determinant that we cannot neglect. So suppose we computed collection of 1 electron orbitals that we can fill with electrons, but we know for sure that in any atom or molecule those orbitals are superimposed in form of Slater determinant to form multi-electron wave function. So with respect to this fact, how do we get total density? Can we get something similar to the wave function absolute value squared, or it will be something more complicated? As soon as we answer this question, our road will be clear. And I probably need to wipe off both boards because ideas will be simple, but it will be a little of calligraphy effort to populate both boards. So here's what we already agreed. If we take functional derivative of the electron-nuclear interaction, then we get a potential, right? It is a subtraction of total energy and kinetic. Whew. density from orbitals. So, in a few minutes, we are going to discuss how to practically find orbitals based on the conversion to the Kohn-Sham parallel universe. But as soon as we already in this universe, we can find one electron molecular orbitals. So since it is not a true universe, we will call them Kohn-Sham orbitals. And the total wave function is formulated as Slater determinant of the first orbital, second orbital, and many other orbitals. We're not going to go beyond 2, otherwise we will die here. So, we need density. If the density depends on all positions of all electrons, many electron density, it will be by definition absolute value squared. But if we need total density as function of only one variable, so the beauty and the goal of all these considerations is to go from many degrees of freedom, many electronic coordinates, only to one. So all the theorems, all our suffering for several weeks is directed towards reformulating very complicated multi-electron problem on one electron language. So we need rho depending on, let's say, R1 order, although we have many very areas. So it means that we need to integrate over dr2, dr3, drn, as many electrons we have. And here we have absolute value square of R1, R2. So we integrate over all but one variable. Good? No violation of basic principles. So we want to merge this definition with definition of Slater determinant. And first we are going to see how it looks for 2 electrons, and then we will be able to establish progression. So how do we formulate Slater determinant? We probably should form a matrix, right? And run indices of orbitals on one axis, let's say columns, and run counting of electrons along the rows. Theta 1, theta 2, theta 1, theta 2. And along the columns we have R1, R2, R1, R2. What should I write next?
Diagonal minus delta.
Theta 2 R2 minus theta 2 R1, theta 1 R2. Correct? Good. So we are going to plug in this expression into here and do integration over R2 because we don't have more variables. And see what happens. This is very simple, a little exhausting on writing, but it will provide very important background for everything we do. So it will establish our own confidence in in this procedures. So if you are taking notes, then go on and concentrate. If you're not taking notes, then you can lean back and wait until the whole board will be populated. R1, integral dr2. And now we are opening absolute value square as two brackets. So this wave function conjugate and wave function without the conjugation. And I'm going to copy what Levi has supported me in writing. Theta 1 R1 theta 2 R2 minus theta 2 R1, thank you, theta 1 R2. No, the same here. Theta 1 R2 theta 2 R2. Okay, and now we are migrating this star sign from above the bracket to inside each of this theta. So if you are following and taking notes, I am very happy and encouraging you to do so. If you are not, you can entertain yourself by reading books. So it's around page 400. What we do. Now we are opening brackets. So we are looking for density as function of one coordinate, integral dr2. And we are opening brackets. So there should be 2 times 2, there should be 4 terms. Theta 1 R1, theta 2 R2, star, star, multiply, theta 1 R1, theta 2 R2, without star. Now, next one. Taking this one, and this one. Theta 1 R1, theta 2 R2, star, theta 2 R1, theta 1, R2. This minus sign. Now, this term is minus sign. Theta 2 R1 star theta 1 R2 star theta 1 R1 theta 2 R2 without stars. And the last term is plus sign. Theta 2 R1 star theta 1 R2 is theta 2 R1 theta 1 R2 without star. So we can, it's too long to complete it at once in the head. Why don't we intellectually focus on each of these 4 integrals and see what comes out. So if you are looking on the first integral, we are having integral dr2 theta 1 star r1 theta 1 r1, and they are not undergoing the integration, so we can write integral after dr2, right? And then we are writing the rest. Theta 2 star R2. We are very close to an insider. Theta 2, R2. So if we are practicing legitimate and loyal solutions of Schrödinger equation, if we are getting good orbitals, they must obey orthogonality. Theta I, theta j, integral dr equals 1 if I equals j, and 0 if I is not equal j, right? Orthogonality. So here, this integral yields 1, because same variable, same index of orbital. Index of orbital. If we are looking on the last integral, so what does depend on R2? Theta 1 star and theta 1. See? 2. Right? So integration applied to these two guys will result into 1 due to orthogonality. So it will be theta 2 R1, theta star, theta 2 R1. So, with plus signs. You can guess, or you can already know the answer by now, that the mid two terms should result in 0. But for confidence, we should double check. So, minus integral. Oh, let's write first what does depend only on R1. And then so minus theta 1 R1, theta 2 R1, first term, and then it is multiplied by integral of these two orbitals, theta 2 R2 star, theta 1 R2, dr2. So, since both functions depend on the same argument, R2, we are allowed to integrate. But since the indices are different, this integral will be equal to 0. So you can, without doubts, cross the whole term. Do you want to practice, or you believe that the third one will be also 0? Also 0. So, what is our conclusion? Rho of R1 is theta 1 R1 star theta 1 R1 plus theta 2 R1 theta 2 R1. So we perform summation over all available orbitals, number 1 and number 2. All of them do depend on R1 only, on the same argument. And conjugate times orbital itself, it will be theta 1 R1 absolute value squared plus theta 2 R1 absolute value squared. And now we can be brave and tell that if we have like Slater determinant as matrix 100 by 100, we still will have the same progression. Summation of orbitals from 1 to highest occupied orbital, they're not molecular orbitals, they are Constant. Fox. And then we write theta I of R1 absolute value squared. Rho. We can forget this index 1 and just tell rho of R. This seems very simple, very natural, but now we do have a proof. So it is not our imagination, it's not approximate like Koopman's theory. This is exact way how to compute total density. So if you have orbitals, they allow to construct density. We are good in time, and now we are almost ready to relax. We have all components. We have our helpful auxiliary universe. We do have And we do have the algorithm how to construct density out of orbitals. What is missing? Nothing. Due to first theorem, as soon as we know density and potential, we do know wave functions. So there is a reasonable way to find them, and I'm going to show it. But based on theorems, we already have solutions. If we would be mathematicians, we would stop here. But we need practical results. So we are missing just little technical protocol, how to get this theta sub I. And then there will be a protocol. So we start with some trial density. From density, we compute total energy. From total energy, we compute the potential, because we know it will be a functional derivative of energy over density. And the potential will be merged together with kinetic energy operator. So number squared. Power square over 2m, but if you are in atomic units, it will be just 1 plus this potential. It will determine an equation to find the orbitals. And then from the orbitals, we are going to find the density, and this density is going to feed into the whole procedure once again. Right? So basically, we already have Kohn-Sham algorithm. We just need to speak about it a few times more so that we get comfortable with it. And we can argue during the questions and answers sessions on the big scientific conferences, when, you know, sometimes people start toasting each other or putting any of your accomplishments under doubts. So you need to be very confident in what you're doing and how to justify it. But we have this step, we have this step, we have this step. We need to speak just a little bit more about how we formulate the Schrödinger equation for one electron orbitals. What are our background, what are our reasons to set it up. And then we have the cycle which goes until we converge to minimal value of total energy. So this was our little exercise of integration. Slater determinants, integration, several terms. First and last stays, middle terms cancel due to orthogonality. So here there is a protocol to compute total density. And I thought I will talk more. Surprise! Surprise for me. Well, we are done. I congratulate you. So we are not mathematicians, but we are done. I think the practical implementations, maybe when I was preparing, I thought to postpone it for the next meeting. So you have enough food for thought to digest. So I am going to distribute pre-recorded instructions for the lab number 8 as a link to YouTube video. I'm going to collect homeworks and your ballots for practicing democracy of what you want to present. And when we meet, there will be, most likely there will be no meeting on Thursday. I may try to set up online, just chatting with you through Skype, giving a lecture, or find a substitute lecture, but please do not mind if there will be no lecture at all on Thursday. And next Tuesday we meet for sure, and we go over practical implementations of this algorithm. How we set up the instructions for a programmer who will do this algorithm, convert this algorithm into code that we all are going to run. So let me just quickly glance before we depart. Okay, so someone wants to cover each of the subjects. So if you haven't completed the density of states calculations in what you submitted here, please do it and send me as an email. I have intentions, from my point of view, they are good, to set up another homework due next Tuesday based on the lab, and it will be built on the homework that we have completed now. So if you have a spare minute, please make this density of states. Because now, if you are on the record, I announce completion of the meeting number 20. Thank you for investing your time. And today was most important meeting of the whole course. You got the core of the theory. Meeting is dismissed. We are going offline, and I will stay here to answer any questions.
Are we meeting across the hall tomorrow then?
I will send an email announcement.
Okay.